Okay, so our new topic is force. So I have three fundamental things here about force that you have to know. So number one, a force is any push or any pull. So if I walk over to you and push you, as weird as that might be, what would that be? A force. What if I walk over to you and I pull you? That's a force. If an object experiences a push or a pull, that's a force. Our unit for force is the Newton. This is what we're going to be using in class. That Newton is the metric unit for force. But I also have here that pound is a unit for force because that's what we use in everyday life. You know, if you talk about how much you weigh, so for example, I weigh 200 pounds, 200 pounds is the force that I exert on whatever I'm standing on. So imagine you lay down in front of me and I stand on you. Now that'd be really weird. If I stood on you, would you feel the force of Spaldo? Yeah. The force of which would be much different than, let's say, my 7-year-old. If my 7-year-old were here, if Maggie were here, and she stood on you, would you feel a force? Yeah, but it wouldn't be as much because she, doesn't weigh as much. So pounds is a measurement of force. Oh, and by the way, the conversion, Newton to pound, 1 pound equals 4.448 newtons. So pounds and newtons do the same thing. Oh, and the other thing I want to mention, a newton is equivalent to a kilogram meter per second squared. And that's very easy to memorize. I'll show you how to memorize that. But a newton is it's an abbreviation for this. This is really what a newton is, kilogram meter over second squared. Okay, number 3. A net force on an object will cause the object to accelerate. Now guys, we don't care about a force on an object. If I were to tell you this object has some force on it, a single force by itself is not going to be significant. What's going to be significant is net force. Now what do we mean by net force? Net simply means total. So for example, look at this diagram here. Say that this force right here, say that one's 100 newtons, and then this force right here is 60 newtons. So focusing only in the x direction, because from here on, or actually from last chapter on, we're breaking the x direction and the y direction apart. So looking only in the x direction, what would be the net force? If you had 100 newtons to the right and 60 newtons to the left, what would that simplify to? That would simplify to 40 newtons to the right. Okay, so net force is what's going to matter. What do net forces cause? Net forces cause what? Acceleration. Okay, in 8th grade, you guys took 8th grade science, which is called physical science, right? And you should have learned Newton's 3 laws of motion. And whenever I teach this, I'm always amazed at how somebody, Isaac Newton became famous for these scientific laws. So just hear me out here. Newton's first law of motion is what? An object at rest, so say my water bottle right here, an object at rest will stay at rest. Dude, I wish that I lived back in Isaac Newton's day, because you could, this doesn't sound very complex, right? And he's famous for it. An object at rest will stay at rest. It's like, duh. And an object in motion will stay in motion. And an object in motion will stay in motion unless acted upon by what? A net force. So some of you said unbalanced, which is unbalanced force is the same as a net force. There has to be a net force, okay? So that's the first law. Second law, Newton's second law. I'm going to put it up here. Newton's second law is the most powerful of his laws, okay? And what it says is that the sum of the forces equals ma. Or another way of saying that is F net equals ma. So those are identical. The sum of the forces and net force, it means the same thing. Just be aware of that. Net force and sum of the forces means the same thing. Okay? And that we're going to use that a lot. That's the second law. The third law is kind of a fun one. The third law, every force has a what? Equal and opposite reaction force. So which means if I walked up to you and punched you right in the nose, well, it'd be my last day teaching here if I did that. Unless it's teacher fantasy day. There's one day, the school board hasn't decided yet, but there's one day where teachers can do whatever they want and there's no consequences. It's called teacher fantasy day. I'm joking. So if I walked up to you and socked you right in the face, okay? So my fist would exert a force on your face, but you'd have the last laugh because your face would exert an equal force back on my fist. Right? Every force has an equal and opposite reaction force. Okay, so those are the basics of forces. Now, all right, free body diagrams and 4 forces to know. So first off, what is a free body diagram? A free body diagram is a special diagram that shows only the forces acting on an object. A free body diagram shows only the forces acting on an object. So here we have a kid pulling on this box, okay? He's tugging on this box with a rope. This is the free body diagram for that situation, okay? So it just shows the forces. And notice, how do we show the forces on the object? The forces are shown how? As arrows. Are forces vector or scalar? Vector. And that's why we draw them as arrows. We show the forces as arrows because they are vector. All right, so let's go through the 4 forces. So the first force is weight. So another name for weight is force of gravity. If you're talking about how much you weigh, you're basically talking about how much force gravity exerts on you. And just look here. W equals mg, right? That's the equation for weight. What is mass measured in? Mass is measured in kilograms, which is kind of weird for some of you, because if you raise your hand if you're coming from AP Chemistry, AP Chem. In chemistry, what do you use for mass? Grams. In physics, we use kilograms. Okay, so mass is kilogram, and then what is gravity measured in? Meters per second squared. So we get this weird unit of kilogram meter per second squared. What's that called? A Newton. Kilogram meter per second squared is a Newton. Okay. Weight is always directed straight down. So see on this free body diagram, which way is the force of gravity or the weight pointed? Straight down. Gravity will never, ever, ever be sideways at an angle. It'll always be straight down. All right, number 2, normal force. Normal force is the force of a surface holding an object up. So see my water bottle again? Is my water bottle sitting on a surface? Yeah. Gravity is pushing my water bottle down, but what's holding the water bottle up? The surface. The name for the force of a surface is normal force. Now, why do we call it normal force? Is it the word normal? Like you probably have told your friends, you're like, yeah, dude, my physics teacher is not very normal. He's in fact, he's abnormal. Is that the type of normal we're talking about? No. What does the word normal mean in this context? In math and science, what does normal mean? Perpendicular to. And don't call it the natural force. For some reason, kids want to call this the natural force. I have no idea why that is. It's the normal force. Normal force means perpendicular to. Is there an equation for the normal force? No, but you'll be able to solve for it using Newton's second law. The sum of the forces equals ma. I'm going to show you in a minute. So normal force, it's always perpendicular to the surface. All right, number 3, friction. So friction, I write friction as a lowercase f. There is an equation for friction. Friction equals coefficient times normal force. So this little guy right here is called the coefficient. Now, the coefficient has no units. There's no units, but it ranges typically from 0 to 1. So here's how you think about it. Think about the coefficient as a percentage. So for example, let's say you're doing a problem and they tell you that the coefficient is equal to 0.1. What is 0.1 in percentage? 10%. So if you're told that the coefficient is 0.1, they're telling you that that friction is 10% of the normal force. What if the coefficient were 0.2? Then friction is 20% of the normal force. Does that make sense? Think of it like a percentage. No unit on the coefficient. It usually ranges from 0 to 1. It could be more. It could be above 1, but usually not. All right, and then what else about friction? Friction, does it ever go in the direction of motion? Are you ever cruising along and then friction pushes you faster? Never. Friction is always opposite motion and parallel to the surface. It says right here. It's opposite motion, parallel to the surface. All right, then the last force. So see this kid right here pulling with the rope? What would we call that force? If you have force in a rope or a cable, that's called tension. Is there an equation for tension? Nope, but you'll be able to solve for it. I'm going to show you how. All right, any questions on this screen? Okay, so let's practice a free body diagram. Okay, here we have a car on a hill. And what I want you to do is you're going to do two separate free body diagrams just to get the feel for how this works. So the first situation, say that the road is frictionless. It's icy. The road is frictionless because there's all this ice on the road. If there's ice on the road and there's no friction, what's the car going to do? It's going to slide down the hill, right? So do a free body diagram for that situation. Then second, say that there's no ice on the road and friction is present and the car is sitting there at rest. So two separate free body diagrams for this car on the hill. I'm going to erase this, and so that's just so you can see what's going on. So here's our hill. So I'm going to draw a free body diagram, put the car on the hill. Here's my car on the hill. All right, so for situation one, where the road is frictionless and the car slides down the hill, what are the forces present? All a free body diagram does, all you're doing is you're showing the forces that are acting on the object. So what do we have on this car? Weight, which is force of gravity. I forget if I mentioned this or not. So look, there's different ways you could label this force here. Sometimes you'll see this labeled as W. W for what? Weight. Other times you'll see this labeled as Fg for force of gravity. The way that I like to do it is I label it as mg, right? What is mg? That's the equation for force of gravity or weight. Okay, what's another force on this car? Normal force. Now, is normal force going to be sticking up like that? No. Normal force, I mean, the whole reason we call it normal, what does normal mean in physics or math?
Perpendicular.
Perpendicular. So there's the normal force. So that would be the free body diagram if the hill were frictionless. Those are the only two forces on the car. All right, now second situation, we have to just add one force. So if friction is present, which way is friction going to be acting? So which way does the car want to move? It wants to go down the hill, so which way is friction going to be acting? Up the hill. And friction is always parallel to the surface. So there's friction. And friction is mu times the normal force. Okay? So free body diagrams, I mean, the whole point of this screen here is just so you can see that free body diagrams show the forces on an object. All right. Everybody got that? All right, Newton's second law. Now, Newton's second law, let's be real clear. What is Newton's second law? Newton's second law says the sum of the forces equals ma, or what's another way of saying that? F net equals ma. And those are both the same. Sum of the forces and F net, same thing. All right, these are the 3 steps that you're going to follow in the Chapter 4 homework set. These are the steps that you're going to follow for pretty much every homework problem. The first thing you do, always, you're going to draw a free body diagram. You have to. Why do you have to do a free body diagram? So you can see what forces are involved in the problem. You got to put it down on a diagram. Second thing you're going to do is you're going to sum forces in the x and y. So again, just like we did last chapter with projectile motion, how are we treating the x direction and the y direction? Separately. They're completely separate. So you got to deal with them separately. So here's how this is going to look. For step number 2, you're going to sum forces x, sum forces y. Now, every problem is different. You're going to have different forces in different problems, but basically it's going to be like this. You're going to look at the free body diagram. You're going to sum up the forces in the x, summity, summity, sum. When you're done summing it, what's it going to equal? ma, or that's an x equation. So basically what you did is you wrote an equation for the x direction. Then you're going to go to the y direction. You're going to have blobbity, 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 blobbity. Why am I saying blobbity? It's different for every problem. Every problem's different. But when you're done summing the forces, what are you going to do? What's it going to be equal to? ma, where that's a y acceleration. So what you've done here is you've created the equations that solve the problem. It's kind of like a write your own equation. You know, remember those books, Choose Your Own Adventure? You ever do those? Remember those books? Like, if you want this to happen, go to page 27. I guess it's not totally that, but kind of like that. It's like write your own equation. Okay, so what's step 3? Step 3, you're going to take these equations that you wrote, solve them for what you're looking for. Okay? So let's go to the last slide. So we'll do an example of this, and then that's it for today. All right, so here's a problem. So we have this boy pulling a 30-kilogram box across a frictionless surface. The tension in the rope is 50 newtons. Calculate the normal force on the box, the acceleration of the box, and the velocity of the box after 2 seconds. So here are your answers. Here are the answers so you can check your work. Number 1 should be 300 newtons. Oh, and this is using gravity as 10. When you're doing the homework set, use gravity as 9.8 because that's what the book uses. So when you check your answer in the back, it'll be right on. In class, I use 10 because it's easier. When you take the AP test in May, they want you to use 10. 10 for gravity. Just because it's easy. Would you rather do like 30 times 10 or 30 times 9.8? 30 times 10. So the College Board tells you use 10 for gravity because it's easier. Okay? The acceleration comes out as 1.7, and then this will be 3.4. So those are the answers. So take about 5 minutes. Try this on your own first, and then we'll go over it. All right, so solving this problem. So step 1, do free body diagram. So I'm going to take away that picture. And let's do the free body diagram right there. So we got this kid pulling this box. So here's the box on the ground. Here's just, that kind of shows the ground. All right, so what are the forces acting on the box? Well, there's always the force of gravity. You can't have an object without force of gravity. I mean, I guess unless you're in the depths of outer space where g is 0. I mean, yeah. Well, you'd have to be like in the far, far, far depths of space. But yeah, you're saying you'll be close to some planet? Yeah.
As long as something exists physically, where's gravity?
Yeah, that's another one of Newton's laws. All objects in the universe attract each other. Ultimately, that's what gravity is. Objects attracting. Okay, so this force here, I'm going to label it as mg. All right, what other force is on the object? Normal force. And normal force is always perpendicular to the surface of motion. And then lastly, we have tension. So tension acts like that, and we're told that it's 50 newtons. Okay, that's step one. Step two, we sum the forces, being sure to separate the x from the y. You know, here's the x direction, here's the y direction. We're treating the x and the y separately. And also, you got to pay attention to sign conventions. To the right is plus, to the left is minus, up is plus, down is minus. So there's our sign convention. All right, so summing the forces in the x direction. What's the only force in the x direction? Looking at our free body diagram. Tension. Is it plus or minus? Plus. Why is it plus? It points to the right. Okay, so I'm going to put this in as 50 newtons. All right? So basically, since there's only one force, that is the sum of the forces. Okay? What does the sum of the forces always equal? ma, where this would be an x acceleration. We just wrote a very useful equation. Okay? Now we go to the y direction. Summing the forces in the y direction, how many forces do we have in the y direction? Two. Normal force and mg. Which one's plus? Normal force. Which one's minus? mg, because it points down. All right, so we have normal force, Fn, minus mg. Okay, that is the sum of the forces. We just summed the forces in the y direction. We added them up. Okay, what does the sum of the forces always equal? ma, where that's a y acceleration. Now, which way will this box not accelerate? In the y. If you look at the situation, you know, this kid is pulling the box across the ground. Is this box going to accelerate vertically? No, it's not just going to all of a sudden like launch into the sky, or into the ground. So there is no acceleration in the y, which means what can we do to our y equation? We can set ay to 0. All right, so everybody got that? Technically, just be aware, technically it's equal to ma, but there is no vertical acceleration because the box is being pulled along the ground. Got it? Yeah. All right, so now let's answer the questions. First question, what's the normal force on the box? You take this equation here, solve it for normal force. Fn is going to equal mg. So the mass is 30. Gravity I'm going to use as 10. And then this comes out as 300 kilogram meter per second, meter per second squared. What's a kilogram meter per second squared? That's a newton. So the normal force is 300 newtons. Notice, guys, I didn't make gravity negative. Why did I not put in a negative 10? Because right here, see this negative right there? I already called mg negative. Why did I call this mg negative? Because it points down. So if you get down here, if you plug in a negative again, you've called it negative twice. So a general rule, once you've summed the forces, you've already dealt with the sign conventions. Once you've summed the forces, you don't have to worry about plus or minus anymore. Just plug everything in absolute value.
Wait, when is second squared?
What is second squared?
When is it squared?
Oh, for acceleration, like meter per second squared.
Oh.
That's acceleration, which really just means meter per second per second. Okay, question 2. The acceleration of the box. So the acceleration is in the x direction. So take the x equation, solve it for a. So a is going to be 50 newtons, and remember, what's a newton? Kilogram meter over second squared, that's a newton, divided by the mass, which is 30 kilograms. So then kilograms cancel, and you get 1.7 meter per second squared. And then lastly, what's the velocity of the box after 2 seconds? That's a motion equation. That's a kinematic. So let's do that. Let's shrink this down. So the way you do number 3, you go V final equals V initial plus AT. V initial 0. Does it say that? You know what? Technically, the problem doesn't say it starts from rest, but you have to assume it does because otherwise it's not solvable. So VF is going to be A times T. The acceleration was 1.7 meter per second squared. Time is 2 seconds. So this comes out as V final being 3.4. All right. So again, the 3 steps: free body diagram, sum the forces for x and y, and then solve the algebra.